So welcome back to the next lecture of satellite communication. So let us have a quick visit on what we discussed in the previous lecture. So we discussed some of the examples related to the Keplerian laws. And if you can recall that if the orbit, if the satellite orbit is a circular orbit, so for the circular orbit, we had an expression that is t square is equal to 4 pi square into r cube divided by mu. So this expression we have obtained from the third law of Kepler, where the value of r is the orbital height from the center of the Earth. We consider it as 42,164 kilometers. That is from the center of the Earth. But if you take from the surface of the Earth, it will be coming approximately as 35,000 something. Okay, and similarly, the velocity. You know that mu is a constant value. So if you put the value of r, then you can find out the velocity. So this represents the velocity at which the satellite is moving at an orbital height of 42,164 kilometers, and the orbit is a circular orbit. Okay. That means this orbit, which is located at an orbital height of this value, this is nothing but the GEO orbit or geostationary orbit. So at this particular orbit, every satellite or every GEO satellite or every geostationary satellite, they are moving at a velocity of 3074.7 meter per second, or we can call it as approximately 3 kilometer per second. That is the speed or the velocity at which the GEO satellites are moving around the Earth. Then we had discussed what is the orbit raising stages. So initially we launch a satellite into a parking orbit. So this is the parking orbit, which is nearly circular orbit. Any question? No. Which is nearly circular orbit. Then from the parking orbit, the satellite will be launched to, not exactly launched, the satellite will be raised to another orbit that is called the GTO orbit, which is geosynchronous transfer orbit. But the GTO orbit is an elliptical orbit, it's not circular. And we discussed that when there is a orbit raising happens from one particular orbit to another particular orbit, particularly remember from parking orbit to GTO orbit, when there is a raising of orbit happens, then it happens at the perigee. Orbit raising happens by using thrust, so velocity thrust, so that is happened at the perigee. Similarly, from GTO orbit to GEO orbit, that orbit raising happens at apogee. Apogee means at this point. Okay, you see the orbit raising happens at apogee. Okay, so this is what we have discussed, and some launch vehicles we have discussed. This is one of the launch vehicle, that is Ariane and GSLV. Ariane is the launch vehicle that the European countries are using. In India, we are using the launch vehicle GSLV. So there are many launch vehicles, not only GSLV. There are different SLV, augmented satellite launch vehicle ASLV, polar satellite launch vehicle PSLV, geosynchronous satellite launch vehicle GSLV. Okay, so many things are there. So these are the pictorial representation of different launch vehicles or different space shuttles you can call, or the rockets we can call, which are carrying the satellites. Okay, if you see this pictorial representation, your satellite is this much portion. the top portion is the satellite. Okay, not all the portion is the satellite. Only this much portion is the satellite, but the rest part of the rocket, these are the dead mass. Dead mass in the sense these parts which carries the fuel and other controlling equipments or electronic components which are responsible to put the satellite into its respective orbit. So once the satellite is kept into the orbit, then all the parts, those parts will be removed. Actually, the parts are not removed simultaneously at a single stage. No, it's not like that. The parts will be removed stage by stage. When the satellite goes from one stage to another stage, some part will be removed. Then in the next stage, some other parts will be removed. Okay, so it happens like this as the satellites move to stage by stage. Then when this multiple stage of launches happen, okay, for example, when the satellite is launched from parking orbit to GT orbit, if we take an example for the sake, what happens? There is a change of velocity happens. But the point, if I show that image back again, the satellite was moving in the circular orbit at a fixed velocity, at a constant velocity, the satellite was moving. Because if we see the Keplerian law, the velocity is can be calculated as mu divided square root of mu divided by r, where mu is a constant, the value of mu is 3 3,98,600 kilometer cube per second square. This is the constant. Okay, you have to remember the value of mu. Only thing is r. So r is the radius of the orbit. So if we take the circular orbit, then r is constant. That means when the satellite is moving in the circular orbit, it is moving at a fixed velocity. That's for sure. Now look at the elliptical orbit. Look at the elliptical orbit. So here in this elliptical orbit, if you see this expression, here r is not constant. For elliptical orbit, this value of r or the expression of velocity will be different. We cannot express the velocity in this particular form. It is only valid for circular orbit, not for elliptical orbit. Okay, so for elliptical orbit, the expression of velocity is something different because in elliptical orbit, the value of r are different. The radius here are different in different locations. Okay, so we know that when the satellites is moving in the elliptical orbit by the second law of Kepler, at the point of perigee, the satellite is moving at a very high velocity. At the point of apogee, the satellite is moving at a low velocity. So the velocity in the elliptical orbits are different. It's not constant. Okay, so in GT orbit, the satellites are moving at different velocities. So when there is a change of orbit, that means from the circular orbit, it was moving in a constant velocity. From the circular orbit, we have to change the satellite to an elliptical orbit. Then we have to apply some thrust over here. Okay, so what we have to do, we have to calculate that if we want to launch the satellite into GTO orbit, then what is the velocity at perigee? Got my point? We have to calculate. That means there will be change of orbit from parking orbit to GTO orbit. So GTO orbit, so this is the point. This point is the common point between parking orbit as well as GTO orbit. Geosynchronous transfer orbit. So this particular point is common for both of the orbits. When the satellite is at this location, then we can say the satellite is in the parking orbit And we also can say the satellite is in GT orbit. Okay, but when the satellite moves in this path, when it reaches here, then we cannot say the satellite is in GT orbit. We have to say the satellite is in parking orbit. But if the satellite moves here, then we can say the satellite is in GT orbit. It's not in the parking orbit. But at this location, we cannot say whether the satellite is in parking orbit or the satellite is in GT orbit. Okay, so this is a common point. So when the satellite was moving in the parking orbit, it was moving at a velocity which was given by the Kepler law for the circular orbit. Then if we try to make the satellite change its orbit from parking orbit to GTO orbit, then we have to find at the point, at the location of perigee, what should be velocity of the satellite. Forget about the parking orbit. What should be the velocity of the satellite at perigee? That we have to calculate not by using this equation, for this equation is valid only for circular orbit, but we have to use the velocity expression for elliptical orbit. If you remember, in the second law of Kepler, I had shown the expression of velocity for circular orbit. So that expression we have to use here. And using that expression, we have to calculate what is the velocity of the satellite in the GTO orbit at a particular location of perigee. Now, what we have to do? So we have to find out the velocity at perigee. So when I talk about perigee, so perigee or apogee, these things are related to the elliptical orbit. In the circular orbit, the concept of perigee and apogee is not there because the radius are same everywhere. Okay, so we have to calculate the velocity at perigee by using the second law of Kepler for elliptical orbit. And we have to find out what is the velocity of the satellite when it is moving in parking orbit. So that velocity, let me represent as a simple v. Okay, so parking orbit is a circular orbit, so I will calculate what is the velocity. So when the satellite is moving in the parking orbit, it is moving at this velocity, which is represented by v. Okay, now this difference v perigee minus v, this gives me the incremental velocity. That means if I want to change the stage of the satellite from parking orbit to GTO orbit, then what additional velocity I require? So that additional velocity is v perigee minus v. So I have to give that much thrust. This incremental thrust I have to give to the satellite, then only it will change its orbit to GTO orbit. Okay, understood that. So come to this thing again. So this del v, so this incremental velocity. So this incremental velocity, when we calculate it, that is nothing but the difference between the velocity at perigee and the velocity in the parking orbit. Now, one more thing is that when some of the propellant, particularly in satellite, where the rocket is carrying some fuels. So some fuels are solid fuels, liquid fuels. The satellite is carrying on it. So those are called as the propellant. So when the propellant are completed, so that particular part will be removed. Okay. So while launching, when the propellant's portion becomes empty, that accordingly the weight of the satellite is decreasing because the fuels or the propellants, they are become emptier time to time or stage to stage. The fuels are become emptier or the fuel weight is reducing because fuels are consumed, so weight is reducing. Hence, we can see in this expression the value of m0, which is the mass of launch vehicle, including satellite. This is going down and down. This is reducing. Okay. So, when the satellite or when the rocket, particularly I'm not talking about the satellite. So at this particular stage, when I say satellite means it consists of everything. It is not about the satellite only. It is not about the satellite. Okay, I am talking about the whole rocket system, whole launch vehicle. Okay, so that mass is represented by m0. So as the rocket is moving, the value of m0 is decreasing, and since the weight is decreasing, the velocity is increasing. Okay, so even without applying external thrust, the velocity of the satellite is increasing. Okay, so this is the velocity, incremental velocity, which is generated by different stages. Then, yeah, so this is the thing why there are multi-stage of launchers. So what happens in multi-stage, each stage provide a thrust and the dead mass of the entire container is removed. So dead mass means, suppose there is a fuel container and if the fuel is over or the propellant is over, it is completely used by the rocket, then that container will be removed out of the rocket. It will be detached from the rocket and it will fall on the sea level. So those are called the dead mass, means any portion of the satellite whose functionality is over with different stages, those are called the dead masses. Then we had a discussion on some conceptual thing that why the launching pads are near east side of any geographical area and why we are launching the satellites towards easterly direction. So these are some concepts we had discussed in the previous class. Yeah, so this is the question. Why launch sites are always east coast of a sea or ocean and launching are always in easterly direction. Okay, so if you see all the launching pads, if you talk about ISRO, if you talk about NASA, if you talk about ESA, so they are near seashore or the sea belt. But only thing is, if you talk about Russia, their launching pad is Baikonur. Baikonur is a desert area. So it's not near seashore because desert area means the population is not there. Okay, so we are preferring either desert or the near sea level because when we are launching the satellite, the dead mass will be fall on the deserts or it will fall on the sea level or on the water it will fall. So this is that answer. Then we had taken one example. Find the incremental velocity required for a eastward launch to place a satellite at 560 kilometer orbit and percentage of fuel saved for this purpose. Okay, so what the question is about, we are launching the satellite towards eastward direction. As you can see in this example, we are launching toward eastward direction. And by doing or by launching the satellites towards east, how much amount of fuel we are saving? Okay, condition is that the satellite will be launched at an altitude of 560 kilometers. Okay, so to do that, what we have done, we calculated the velocity at which the satellite or the velocity at which the Earth is moving around itself. So that is given by 2 pi r, where r is the radius of the Earth, which we have considered as 6,378, divided by the time, how much time the Earth takes to complete 360-degree rotation. So this duration, it is in second, and it is called as 1 sidereal day. So one sidereal day is nothing but 23 hours, 56 minutes and 4 seconds. So this ratio gives us the amount of the velocity at which the Earth is moving around itself. So what I mean to say that even I am an object, or my house is an object, or my university is an object which is on the surface of the Earth. It seems to be stationary, but actually as the Earth is moving around itself, all the objects on the surface of the Earth are moving at a velocity. Even if they are stationary, they are moving at this velocity. But if that object is in motion, then the velocity will be something different that we can calculate by using relative velocity. Okay. So suppose I want to launch a satellite at an orbit of 560°, then how much velocity? So we know that velocity is equal to square root of mu by r. And what is the r? R is the radius. So here it is given the orbital height is 560 kilometers. So 560 kilometer means from the surface of the Earth, it is located at 560 kilometer. So if we include the from the center of the Earth, then you have to add 6,378. So what we will have here, you see, I have calculated v square is equal to mu by r, or v is equal to square root of mu by r. In place of r, I have written 6,378 plus 560. That means if this is the Earth, okay, and this is the satellite, so this distance is 560 kilometer, and this distance is 6378. So suppose this is the orbit of the satellite. So the orbital height is always calculated from the center of the Earth. So that's why we have added the radius of the Earth with the orbital, with the latitude, with the altitude of the orbit. So using this, we found out that the velocity at which the satellite moves is coming out at 7.579 kilometers per second. Okay, got the point. That means what we have calculated, if we want to launch a satellite at an altitude of 560 kilometer, then the satellite will move at a velocity that is 7.579 kilometer per second. Okay. Now, let us think what else is given in this example. We are launching the satellite eastward direction. We are launching the satellite towards eastward direction. So when we are launching the satellite towards eastward direction, and you know our Earth is moving from west to east. Okay, so by default, see, the satellite will be launched towards east direction. The Earth is moving towards east direction. So by default, the velocity at which our Earth is rotating, so that velocity is a by default velocity what the satellite is gaining. Even if the satellite we have not launched, the satellite is on the surface, satellite is kept on the launch pad, the default velocity of the satellite which that attains is equal to this value, even if the satellite is not launched. And if we want to launch the satellite at an orbit of 560, we calculated the velocities at which we should launch, that is equal to this. But the satellite by default attains this velocity. This is the required velocity. So what is the incremental velocity, or what is the additional velocity we require? So this velocity minus the by default velocity which the satellite is gaining by the velocity of Earth. You subtract this, then it will give us the incremental velocity. That means what? If you want to launch a satellite, so I will show it here. I have subtracted that. So this is the velocity now at which we should launch the satellite at an altitude of 560 kilometers from the surface of the Earth. Okay, so we don't need this velocity. We don't need this velocity. We need the satellite to launch at this velocity, not this velocity. So how much savings we have done? We are saving this much velocity. So then we can calculate how much amount of fuels we have saving. So this amount of fuel. So it is actually the velocity which the satellite is gaining by the rotation of the Earth. So this amount divided by this value 7.579. Okay, into 100 if you do, so that is it is coming at 6.13%. So this much amount of fuel we are saving. So what I wanted to tell that consider the Earth is stationary. That means the Earth is not rotating. It is completely stationary. Keep it in mind. I'm very in detail. I am explaining. Assume the Earth is stationary. It is not moving around itself. And we want to launch the satellite at an altitude of 560 kilometers. At this altitude, at this orbit, we want to send the satellite. Then how much velocity we need the satellite to launch? At what velocity the satellite should be launched? The answer is 7.579. This is the answer. Now, since the Earth is rotating from west to east, and we are launching the satellite towards east, so the velocity at which we launch the satellite, that is this minus this, that is equal to this. Now I am just twisting my question. I have a different question related to this. Suppose my question is, suppose I am launching my satellites towards west direction. Okay, the Earth is moving from west to east as it is at a velocity of 0.465 kilometer per second. But I want to launch a satellite towards west direction and at the same altitude, that is 560 kilometer from the surface of the Earth. Okay, the difference is that the Earth is rotating from west to east, but I want to launch the satellite toward west direction. So what should be the velocity at which I should launch the satellite? So this is nothing but 7.579 plus 0.465. You have to calculate the relative velocity because the Earth is moving towards east, satellite is moving towards west. They are just opposite. So what is the velocity? 7.579 plus 0.46465. So whatever the result you will get, so that is the velocity at which we should launch the satellite towards west direction. Okay, so if you calculate what it will be coming, it will be 417 plus 74108. So 8.044 kilometer per second. So we have to launch the satellite at a velocity of 8.044 kilometer per second if you want to launch the satellite towards west direction. So here, if you calculate the amount of fuel, where we are not saving fuel because we are launching at an additional velocity. So we need additional fuel. So how much additional fuel we are consuming by launching the satellite towards west direction? What is the extra fuel the rocket is consuming if you launch towards west direction? This is nothing but 8.044 minus 7.579. So it will be coming as same value, that is 0.465. Okay, so this 0.465 divided by 7.579. If you multiply by 100, if you'll do, so you will get 6.13%. So this much percentage of extra fuel we are, or the rocket requires when you launch the satellite in the opposite direction, that means in the westward direction. Okay, now see, we have done two calculations. In one calculation, we have seen that by launching the satellites towards east direction, we have 6%, approximately 6% of fuel saving. But if we are launching towards west direction, we are requiring 6% of additional fuel. So that is the answer, that why the satellites are launching towards eastward direction, because of saving this much of fuel. Okay, so that was we have uh, the understanding what we gained from the launching of the satellite. Now let us come quickly to an example that when we are launching the satellite in different stages, that means when we are launching the satellite from parking orbit, from parking orbit to GTO orbit, from GTO orbit to GSO orbit. So what is the incremental velocity, or what is the thrust velocity we require? Okay, so assume that it is given the parking orbit is located at an altitude of 560 kilometers. Okay, so I told you how to calculate. Yeah, the first hint it is given parking orbit to GTO orbit is done at perigee. But whether, let me see, yes, figure is here. I am again explaining how to do it. See, here we have two stages. First stage number one, this is stage one. We are launching the satellite from parking orbit to GTO orbit. So this orbit, the red orbit is the parking orbit, and this blue color orbit represents the GTO orbit. And when we are launching the satellite from parking orbit to GTO orbit, it happens at perigee. So that means this point. At perigee, it happens. And question is to find out what is the incremental velocity required. So first we have to calculate what is the incremental velocity required from parking orbit to GTO orbit, then incremental velocity required from GTO to GSO orbit, or that is GEO orbit. That means what is the additional thrust we should give, or what is the additional velocity the satellite should attain so that it will change the orbit. That is the question has been asked. How we can calculate? First, we have to calculate at what velocity the satellite is moving in parking orbit. Given the orbital height is 560 kilometers, that we have calculated in the previous example. See, this is by, since it is on circular orbit, we have used this expression and we got the velocity 7.579 kilometers per second. Okay. Then what we have to do? We have to calculate if the satellite is moving, because we have to change the orbit. So that now my next orbit is GTO orbit. So GTO orbit, at what velocity the satellite should move? And we know that when the satellite is moving in an elliptical orbit, the velocity of the satellite is not fixed. At a point of perigee, the satellite moves at a high velocity, but at a point of apogee, the satellite moves at a low velocity. That was given by Kepler's second law. The area swept by the satellite at any point in the orbit or any certain time duration is equal. This is the second law of Kepler. And we had a conclusion from that. At point of perigee, the satellite moves at a high velocity. At point of apogee, the satellites, this is apogee point, the satellites moves at low velocity. Okay, so since this particular point is common for parking orbit and GTO orbit, so we have to change the stage of the satellite at this particular point. From this stage only the satellite will change its orbit. So we have to calculate at perigee what is the velocity of the satellite when the satellite moves in the GTO orbit. And we have to find out the difference, the velocity in parking orbit minus velocity at perigee. So that will give us the incremental velocity. So if you want to change the orbit of the satellites, so we have to increase the velocity of the satellite at this point by that amount so that the orbit will be changed. Got the point? Similarly, in the second stage, when we want to change the orbit of the satellite from GTO to GSO, it is done at apogee, because apogee is the point which is common in between GTO orbit and GSO or GEO orbit. So the orbital change happens at apogee point. We have to calculate at what velocity the satellite is moving at apogee, because we know at apogee satellites moves at a low velocity, that we know. So we have to calculate that velocity, and we have to calculate the velocity of the satellite in GEO orbit. So what the difference when we calculate the velocity at apogee, particularly for GTO orbit, you have to keep it in mind that this GTO orbit is an elliptical orbit, and you have to use the formula of velocity for elliptical orbit. Okay. Now, when you want to change the orbit from GTO to GSO, so we have to calculate the velocity at which the satellite will move in GEO orbit, whereas the radius of GEO orbit is known to us, that is 42,100 something. Okay. So GEO is an circular orbit. It's not an elliptical orbit. So when we calculate the velocity in the GEO orbit, it's a in GEO orbit, the satellite moves at the same velocity. The velocity does not change. Okay. So it's a circular orbit. So we have to use the formula for circular orbit. So what do we have to do when we have to find the incremental velocity? So first of all, from parking orbit to GTO orbit, we have to calculate the velocity at perigee minus the velocity at which the satellite is moving in parking orbit. So this difference will give us the incremental velocity when the satellite moves from parking orbit to GTO orbit. For the second stage, when the satellite changes its orbit from GTO orbit to GSO orbit, then what is the additional velocity we require? That we have to calculate the velocity in the GEO orbit minus velocity at apogee. So one thing I must tell here is that this parking orbit is an circular orbit. This GEO orbit is also an circular orbit. Whereas this one, when we calculate V perigee, when we calculate V apogee, they are not circular orbit. They are elliptical orbit. So the velocity, when we calculate the velocity at perigee and when we calculate the velocity of apogee, then you can observe that even if perigee and apogee both points are located on GTO orbit, so both points are having different velocities. That you can observe. Okay, so let us, if you understood this, let us do the calculation. So first point, I will calculate velocity in parking orbit, velocity in perigee. So while calculating velocity of parking orbit, I will use the circular orbit. When calculate perigee, I will use elliptical orbit. See here. So velocity in parking orbit, this one is this square root of mu by r, that is 7.579. This one we already have calculated in the previous one, 7.579. I will show it because orbital height is same now, 560 kilometer. So for 560 kilometer, you see we have calculated here. You see 7.579. Okay. So the same thing, it is coming here. Now what you have to calculate the velocity at perigee. So you see the formula. It's not the same formula what we have used here. This formula is quite simpler because it is a circular orbit, but this formula is not simpler. It's for elliptical orbit. Okay. And for elliptical orbit, when we calculate this, what is this R? This R represents the perigee, or that is called R perigee. That means if I show this example at perigee, your R is this much from the center of the earth to the perigee point. And we know that from this point or surface of the earth to this particular point or the orbit, this distance is how much? 560 kilometer. This is 560 kilometer. That is the orbital height from the surface of the earth. And the radius of the earth you have to include, that is 6,378 kilometer. That is the radius of earth. So you have to include both the distance. Okay. So that will give us this R value. Whereas A value, A is the eccentricity. So what is A? A value is this distance plus this distance divided by 2. Okay, that means from the center of the earth to perigee, how much is the distance? From the center of the earth to apogee, how much is the distance? So first of all, from the center of the earth to perigee, this distance is 560 kilometer plus the radius of the earth, that is 6,378 kilometer. So this summation gives you the orbital height of perigee. How we can calculate the orbital height of apogee? It is not given. How we can calculate? If you see the apogee point is a common point in between the GTO orbit as well as GE orbit. Okay, so what you can observe here, so this point apogee, it is nothing but, that means this distance is nothing but the orbital height of GEO orbit, which is 42,168 or something. I don't remember. Let us see here where we have used it. Here, this one, 42,164, this value. So this is not 68, it is 64. So this much. This is the orbital height of GEO orbit. So it is known. Even if it is not given, you have to apply your mind and you have to decide what should this value be. Okay. So now you use it in this here, in this expression, and it will be coming as this value. So when the satellite changes from parking orbit to GTO orbit, what is the incremental velocity we require? The 9.933 minus 7.579, which is coming as around 2.354 kilometer per second. So this is the additional velocity we require the satellite to change its orbit from the parking orbit to GTO orbit. So this additional velocity can be obtained by using an additional thrust. And when we apply additional thrust, that can be obtained by pushing some of the fuels from the rocket towards backward direction. So if we push the satellite with a high velocity, and that additional velocity is 2.35 kilometer per second, this can be attained by pushing some amount of fuel uh, of the satellite towards backward direction. So this additional velocity can be attained. Okay, this is the additional velocity required for the satellite when it changes from parking to GTO. The same calculation you will do here. From this is what, from GTO to GEO, or change of orbit happens. So when we are changing from GTO to GEO, at which location the orbit changes? At apogee. We are the stage changes at a point of apogee to GEO orbit. So we have to calculate the velocity at apogee. Now, if you see, or let us discuss this in the next class, because we have completed the duration. We will continue this example in the next class. If you have any question, then you can ask.